Good morning. Welcome to Krishna's class. The topic that we discuss today is so-called measure spaces. Measure spaces are measurable spaces with a measure defined on it. Now, before we come to that, I'll revisit the proof of the theorem that I introduced in my last lecture. So we did an approximation theorem, namely that all measurable functions, measurable non-negative functions can be approximated from below by a sequence of simple measurable functions which are monotonically increasing and bounded by the given function, with the property that the sequence of functions or the sequence of simple functions that we have constructed has the property that they converge to the given function at every point. Okay. Now we are talking about extended real valued functions. Therefore, the points where the function takes the value plus infinity, there S and X becomes the sequence 1, 2, 3, etc. N, that is the sequence N. So as N tends to infinity, N goes to plus infinity. So in that sense, it converges at that point also. But actually, in our usual parlance, it means the sequence diverges to infinity. Okay. So recall the statement of the theorem. You have X, M, a measurable space. M is the sigma algebra on that. F from X to the extended non-negative real line, that means 0, infinity, infinity included, be measurable. Then there exists simple measurable functions Sn such that 0 less than or equal to S1 less than or equal to S2, etc. That means it is a monotonically increasing function, but all these functions are bounded above by the given f. Yesterday I explained it very detailed. And then there is the property that S and X converges to f of x as n tends to infinity for every x belonging to x. That means the sequence S and x, the sequence Sn point-wise converges to the given measurable function. This is a very handy tool because it says every measurable non-negative function can be approximated from below by a sequence of measurable simple functions, which is monotonic. All this is very significant while we define the integral of f. Okay. So let us recall, I wanted to give a clarification about the proof of a part of some point where towards the end I made some noise about the proof, and maybe some people are not clear enough about how the whole thing is. So recall that we split the interval 0 to infinity as 0n and n infinity. Okay, and then the interval 0n is written as union k equal to 0 to n 2 to the power n minus 1 of the sequence of intervals k by 2 to the power n, comma k plus 1 by 2 to the power n. I mean, these are all disjoint intervals. So that the whole 0 infinity can be written as the union of these set of intervals along with the interval n to infinity. We give a notation akn, or we define akn as the f inverse of these intervals. Now f is measurable. Therefore, you see that f inverse of k by 2 to the power n, k plus 1 by 2 to the power n is designated by akn. Akn becomes now measurable. Similarly, an we designate we use an to designate f inverse of n to infinity. Therefore, now we are in a position to define our Sn. Sn is defined as sigma k equal to 0 to n 2 to the power n minus 1, k divided by 2 to the power n, chi akn. That means on akn, we take the value of this to be k by 2 to the power n and outside 0, and then you sum it up altogether plus n times chi an. So this is the step function that we constructed. I have explained to you how we do the construction. Then we wanted to, then of course, the very definition tells, or the way in which we have constructed, it's clear that the condition A is valid. It's a monotonically increasing sequence. Now we want to show that for each x on the interval 0 to infinity, Sn x converges to fx. How do we prove that? Now this is the part I want to explain to you. Now assume, see, x can be of two types. One, either x can be such that fx equal to plus infinity. Okay, that is the first case. That means a function of this kind, something like this, so that this is the x that you have, this is f, then fx turns out to be plus infinity. Otherwise, at other point, I mean, or maybe x takes a fx takes a finite value. So these are the two distinct possibilities. We take up both separately. Suppose x is such that fx equal to infinity. Then you see that Sn x, by definition, it is on this part, you have the value of Sn x taken as n. Okay, recall the construction. For every n. Therefore, what you get, this sequence is fine. And you see that this sequence turns out to be 1, 2, etc. So 1, 2, this is the sequence. Now this sequence actually, as n tends to infinity, diverges to plus infinity, or we shall say, in this case, converges to plus infinity. So that point has been taken care of. Now we take the case where x is such that fx is finite. If fx is finite, see this is x, say, and this is your fx. If fx is finite, fx is less than some positive integer n. Okay, it is bounded by an integer n. Now, by our construction, for every n greater than n, there exists a k such that fx happens to be in this, or x turned out to be in this is the same as x belonging to a, what is our notation? Okay. So fx is lies in this. So what does it mean? And what is your Sn x at this point? At this point, on akn, your Sn x is defined as k divided by 2 to the power n, and that is bounded above by f of x. Check the construction. Now you see that Sn is an increasing sequence. So we compute fx minus Snx. Now what happens is, see, if you refer to the figure, so you have a certain interval into which fx belongs to, and this is the value of Snx. So fx minus Snx is less than the length of this interval, and therefore you see that fx minus Snx is less than 1 by 2 to the power n, which is the length of this interval. Okay. Now, and this is true for every n, so that n greater than n. What happens is this. Now, fx minus Snx is less than 1 by 2 to the power n, and fx minus Sn plus 1x is less than 1 by 2 to the power n plus 1, and so on. Okay. Therefore, as n tends to infinity, this 1 by 2 to the power n goes to 0. And what does it mean? It means Snx converges to f of x as n tends to infinity. So for every n greater than capital N, you have this inequality. So as n tends to infinity, this turns out to be fx Snx converges to f of x. That's the proof of that. So that's the second part of the statement. Okay. So I just leave it at that, and now we introduce what are called the measure spaces. Okay. So what is a measure space? Now we are bringing in the concept of measure, or in other words, we are asking, we have already prepared the ground. What do we call a measure on a measurable space? Or a measure let us recollect the Lebesgue measure story. What did we have? We had the real line to start with, R. Then we had the class of all measurable sets on R, which we called the Lebesgue measurable, which was constructed in such a way that it was to include all the intervals, and then whenever we had intervals, so we see all intervals were measurable. And this is a sigma algebra which contains all intervals. In fact, all open sets. In fact, the usual all the open sets in the usual topology is there. Therefore, it's a huge collection of sets. At the same time, we also observed that this does not take care of all the subsets of R. And then on that, we introduce the measure. What is the measure? The measure we introduced was the following. That is, measure of E is greater than R. E is an element of the sigma algebra that we have expected. Then this had the nice property that when En is a disjoint collection, we had that means countable additivity was assured in this. So the measure of the union is equal to sigma n equal to 1 to infinity measure of n. So this is what is called countable additivity. We had some more extra conditions here. So our Lebesgue measure was an extension of the okay. The Lebesgue measure was an extension of the concept of length for an interval. So we were generalizing length, the concept of length, to introduce, or in other words, introduce a concept of length for sets which are not necessarily intervals. So if E is an interval, measure of the length of, that was another condition that we have imposed, right? So let us we are now trying to generalize this idea. Okay, so Lebesgue measure was a very specific measure defined on the see the length of So the Lebesgue measure was a generalization of the concept of length, and it was a with a very specific objective. Now we have generalized, and we are not worried about all such aspects because we may not have the set X, may be something arbitrary, where you are talking about a class of subsets which may not have any structure to support any of the statements that we are making here, except this one. So what is the desirable property which depends only on a set theoretic union that is valid? So what would be a measure? How do we define this? So first of all, we observe that non-negative set function defined on the sigma algebra. So we are now identifying measure as a non-negative set function. That means we have the map uh, designated by mu. Mu is a map from sigma algebra the extended real line, non-negative extended real line given by associating with each element of script m a number. That is the first thing. The other crucial property that we would like it to be true is this. If an is a subcollection of n, that is ANs are all measurable sets with respect to sigma algebra that we have introduced on X, such that is disjoint. So it's a disjoint subcollection. That means AN intersection AM then you know that the union of AN is a measurable set. It's an element of the sigma algebra. So you have mu of the union defined, and we want this mu of union AN, want the property mu of mu of A. That means mu is countably additive. And you cannot have these kind of things. I mean, does not make any sense because we are now not working out a specific measure except that we define a mu in some way. Whereas in the case of a Lebesgue measure, we were seeking a extension of the notion of length and attributing a length to as large a class of subsets as possible on R. And we found that this cannot be done satisfying all the conditions that we have stipulated there. So there are some sets left out which you call non-measurable. And all the measurable class of sets form a sigma algebra in that case. So this turns out to be the crucial condition that these two things, mu is a map from script m to 0 to infinity. Now we assume that there exists some A, at least one A such that mu of otherwise what happens is if on the whole of m mu takes a value infinities, okay, then it doesn't serve any purpose. Okay? For the future work of developing integration, that does not serve any purpose. This is to trivialities. In the Lebesgue measure, we had certain further specifications, and that brought in some conditions on the choice of the so-called measurable sets. So it is a working backward. Okay, we had a feeling of what our measure should be, and from there we constructed a suitable measurable class of sets. Okay, and that happened to have a sigma algebra structure and so on. So here what we have is we are starting with X with a sigma algebra on it. Then we introduce a function m, mu. This is the sigma algebra. Mu defined from m to 0 infinity included, having the property that so mu is non-negative. Countably additive set function defined on the sigma algebra Thus, what we have is we have the set X with a sigma algebra of subsets, and now a non-negative countably additive set function. When you say countably additive, see, this condition is important. This joint. Now you see that when you take two overlapped intervals, then their union, if their union is in an interval, then the length of the union is less than or equal to sum of the lengths of this. And this may not be equal. That's the problem. Okay. So this is important in the condition that this is a when we say something is countably additive. When we say countably additive, we are taking the sequence an of measurable sets, which is disjoint. Set disjoint condition. That is it. It's a disjoint collection. Elements of it's a countable collection. That's important. So this is important when we talk about what is called a countable additivity. So let us now look at what it implies. So a measure space is these three: X, a sigma algebra, and a measure. So then you call this a measure space. Already we have imposed mu, and you can impose any non-negative set function on M with this countably additive property, and it becomes a measure. Okay. So there are different measures that you can impose, as there are different sigma algebras that you can choose. Essentially, the choice of the sigma algebra and the choice of the measure are going to be decided by what exactly you want to do. So that's our process. Okay. Now let us look at the consequences. Now we will, before that, this is what is called non-negative measure. Now we define what's a complex measure. This also we shall require later. Let us define what's a complex measure. A complex measure is a complex value countably additive set function defines the sigma, or rather we will write it as on a sigma. So what we have is this. There is x, there is a sigma algebra, and then mu. Now mu is now a map from C, which is countably additive. Exactly satisfying the same requirements. Okay, so that's the definition of a complex function. So we can talk about real measure and complex measure. Okay. Right. Now let us look at the consequences or the properties of this. So we have the following theorem. Let this is called measure space. Before we put in the measure, it is called a measurable space. That means it's fertile enough to introduce a measure on it. Okay. That means xm is called a measurable space. xm with a measure mu is called a measure space. Okay. That's the difference between a measure space and a measurable space. Then we have the following. First one is the measure of the empty set. Zero. Because you know that if M script M is a sigma algebra, then it contains both X and its complement, namely the empty set. So we are asking what exactly should be empty set, and it is desirable to, or it is rather the conditions that we have set in on the measure assures that the mu of phi or the empty set is equal to 0. We are on the right track. The measure of this measure is mu is finitely Third property is this. Where of course we say pairwise disjoint just for clarity and right. Third property is this. If B it is A, comma B, then P of third. The fourth property is this. U of A AI and that means this is a, so you have A1, A2 is a superset of A1 and so on. AN plus 1 is a superset of AN. They are all measurable sets. And if that is the case, and if A is equal to N equal to 1 to AI, then AN is, then mu of AN goes to mu A as N goes to. We will discuss it later. Mu AN mu A as N tends to infinity if A equal to N, where AN is not complete. I have to put one more condition, and etc. with mu A1 fine. A1. Okay. Now let us work out the proof. The first one, which says mu of 5 or the empty set is equal to 0. Let you know that we have assumed that there exists a set A with the property that mu of A is finite. Take define A1 equal to A. All these, you take A2, A3, etc. are all empty sets. Then we have mu of A, because you see that you have this is a, you can say it's a disjoint collection, and therefore mu of A is equal to mu of A plus and they are all mu of 5. Okay, therefore this is equal to and this relation of mu of A is finite, therefore this implies mu of zero. So that completes the proof of A. B. In this case, we look at this relation. We have infinite. Yeah. Now this is a disjoint collection. Now what we do is the following. In this relation, an plus 1, an plus 2, etc. are all taken as the empty sets. Then you know that mu of an plus 1 is 0, mu of an plus 2 is 0, etc. Therefore, in that case, what you get? Mu of plus etc. They are all empty sets, and this is equal to sigma k equal to 1 to n. And this is exactly what we wanted. Okay. And we have mu of empty set is equal to 0 from the previous part of the theorem. Now the third one. So it is finitely additive. Okay. It's countably additive implies finite additivity also. So disjoint connections. Now what we want is to prove the third statement is that, so let such that A is contained. So you have this situation. So you can split B, you can write B as A union B minus. Okay. Now clearly A intersection empty. Therefore you have mu of B, and this is measurable. B minus A is also measurable. Okay. Therefore you have you have B minus A mu B equal to mu A plus mu of, and this is of course greater than or equal to mu of, because this is non-negative. Therefore, you see that this is greater than or equal. So that completes the proof of third assertion. Now we have two more assertions. True. D is, what we have is this. We want to say that mu of A, where A equal to infinity, if A equal to union and these are all elements of script M. And you have A1, it is the response. Okay, so what do we write? Okay, so we put see the this is your A1 and this is A2, this is A3 and so on. So you call this B1 and then A2 minus A1 you call B2. Then call this B3 and so on. So B1 equal to A1. Set Bn into okay. Then they are all measurable sets. And also you have Bi and T whenever I is not equal to 0. So you have An equal to B1 union B2 and Bn. And A is given by union I equal to 1 to n Bn. This is a disjoint unit. Therefore, what do you have? Which implies mu of A sigma I equal to 1 to infinity I equal to 1 to infinity of and what about mu of An? Yeah, mu of Bi. Therefore, what do you have? Consequently, okay, which is equal to Bn and 1 to infinity, which is equal to mu of one. You can write one more step. This is an. We started with that. So let's so the next one statement is a qualified statement. It says now the condition is the following. A is given by intersection equal to 1 to an and an scripted, and you have a1 these are the conditions. This is the statement that we want to put. Now to prove this, see what we have is this is a1, a2, etc. and so on. So it is telescopic in nature. And we assume mu of a1 is finite. Now you see that a is equal to intersection a. Now define Cn equal to a1 minus a. Then what you get is we make it into a situation where you can possibly do this part. Then C1 is contained. C is contained in. So mu Cn equal to mu of a1 minus a, because an is contained, and which is equal to, so a1 minus an is equal to union Cn, and hence applying D we get mu of A1 minus mu of A equal to mu of A1 minus A, which is equal to limit n tending to infinity of mu of Cn. Mu of A. That means, which implies mu of A. That's what we want to do. Okay. So let us now look at some examples. And especially in the part C, we had put a restriction that mu of A1 is finite. Some examples. First example, let E be contain some x. Define mu of E equal to infinity if now define mu E to be the number of points or what you call the cardinality if E is a finite set. Now this you can verify that then mu is a measure. With the sigma algebra, taken as the power set of can verify that all the conditions are satisfied. Then mu is called the counting measure. So in problems involving say probability theory and so on, this counting measure becomes significant. So I am not too familiar with the probability interpretations of measure except just the cosmetic way in which so that one of the origins of pressure theory is from requirements in probability. Second example is fix now define UE equal to 1 if x dot belongs to otherwise that is equal to 0. Now this is a measure which identifies whether a particular set contains a given element. Okay, right? It's a sort of what you call a signature of set, whether it contains x naught. Then you can easily show that this is a measure called the unit mass concentrated one can easily check that all the conditions of mu being a measure are satisfied. Take the third example. The third example is significant in the context of the statement E of the theorem we have just now proved. Let mu be the counting measure discussed in A on the set. Take all the natural numbers. Let A and be defined as that is n plus 1, etc. That means you omit the first n minus 1 terms. This is the empty set. And mu an etc. That means all these ANs are having infinite measure. At the same time, their intersection is the empty set, and its measure has to be equal to 0. Now you have therefore mu an equal to infinity. Yes. This shows that E is not valid. And we had another condition in E. What is that? Thus, the requirement that what was the condition that we had? Mu A1 is fine. Choose that. Essential for the validity of the above theorem. Here mu A1 is infinite. Therefore, we cannot apply this. Okay. You see that mu A1 is infinite. That's the problem. So this is not something which can be altogether removed from theorem. I think I will stop here. Let me conclude today's lecture here. So thank you very much.